Good day, everyone. Today, I'm going to discuss all about the hydrohalogenation of alkenes. This is quite challenging concept under organic chemistry subject, but I'll try my best to explain this as clear as possible so that you can easily understand this topic. So let's start. First things first, we're going to set our objectives for this micro lecture. This lecture will focus on first the basics of hydrohalogenation, and of course we're going to discuss about hydrogen halides, and lastly the main topic, which is the hydrohalogenation of alkenes. But let's first unlock our vocabularies and familiarize ourselves with these common words that we're going to use in all throughout this lecture. First, nucleophile, electrophile, alkenes, protonation, pi bond, and lastly hydrohalogenation. Now, let's familiarize ourselves with the difference between a nucleophile and an electrophile. When we say nucleophile, these are the atoms that has electrons and are negatively charged, meaning they are very much willing to donate an electron to another atom or to another compound. On the other hand, when we say electrophile, these are atoms or compounds that has partial or full positive charge. For example, in the diagram, we can see that there is an excess positive charge here that is very much willing to accept an electron. So if we connect these two terms or these two diagrams, we can see that the bromine here has negatively charged, which can connect to the carbon atom here that has positive charge. So we can conclude that the process always starts with a nucleophile that goes or donates an electron to an electrophile. Next, we have alkenes. As we all know, alkenes are unsaturated hydrocarbons with at least one double bond or multiple double bonds. So we have been very familiar with this term since this is very common in organic chemistry. So in the diagram, in the picture, we can see that there are two carbon atoms here and here, which is connected by a double bond, making it an ethene. So when we have two carbon atoms connected with a double bond, we call it an ethene. So that's it for an alkene. This is the basic knowledge that we need to know in an alkene. Next on the list, we have protonation. When we say protonation, this simply means addition of proton. This is a process by which a proton was added in a certain atom. Let's say, for this example, we have an ethene here. The ethene that reacted with a hydrogen halide, in which the halogen is unidentified. Then, when this reaction takes place, when this hydrogen here already attached itself to the carbon here, the double bond between these two carbons will be broken, which will result to the addition of proton in this carbon here. So this carbon will be positively charged carbon. This process is called protonation. I'm going to discuss more about this when we jump to the hydrohalogenation process itself. But let's first unlock our vocabulary about pi bond. Pi bond simply means double bond. So in this picture we have an ethene. This is what we call a pi bond, double bond. So going back, we already had the basics of hydrohalogenation in our objectives. So first objective was already checked. So now let's jump to what a hydrogen halide is. So hydrogen halide, unlike halogens, are polarized molecules which easily forms ions. Hydrogen halides also add to alkenes by electrophilic addition. So in this picture, we can see a reaction that happens between an ethene and a hydrogen halide. This is what a hydrogen halide is. This is a hydrogen halide. So when this hydrogen halide is added to an alkene, so this is what the product would be. You have a hydrogen added to the first carbon, then the halogen added to the second carbon, which will create an alkyl halide. The addition of hydrogen halides to asymmetrically substituted alkenes leads to two products. This is shown in the second picture, which tells us about how a protein in hydrogen bromide reacts with each other. So as we can see, this is an asymmetrical alkene because at one side we have two carbons, while on the other side we have one carbon only. Then when this propene reacts with this hydrogen bromide, we can create one bromopropane, which will be our minor product, and two bromopropane, which will be our major product. But later on, I'm going to discuss what we should follow in creating the product for this reaction. So we are done with the basics of hydrohalogenation. Now we're also done with the hydrogen halide. Moving on with our discussion, I will now give you examples of the hydrohalogenation process. But first, let's deal with a simpler one. Here we have an ethene that reacts with a hydrogen halide. The X here is represented by any of these four halogens. It can be fluorine, chlorine, bromine, and iodine. Next, this happens, the protonation process. Because the hydrogen here already attached itself to the carbon here, the double bond between these two carbons will be broken. Once it does, a proton will be added to this carbon here. This will attract the electron in the halide, in the halogen, and this will result to this compound. We have the halide here connected to the carbon here, and the hydrogen atom connected to the carbon here. But to clarify, since this is a symmetrically substituted alkene, this two can be placed to any of this carbon. we can have, let's first erase this. We can have the hydrogen atom connected to this carbon, and we can also have the halide connected to this carbon. It won't matter. It will still be correct because this is an ethene is a symmetrically substituted alkene. So yes, you may say that the hydrohalogenation of alkene might be a bit easy, but that is only when we are dealing with a symmetrically substituted alkene. But the main challenge would be, what if the alkene is asymmetrically substituted? So this will be a bit confusing, but at the same time would be very satisfying when we already understand the process. To explain how to correctly write the product when we are dealing with an asymmetrically substituted alkene subjected to hydrohalogenation, we should always remember the Markovnikov rule. This rule states that when a hydrogen halide is added to an asymmetrically substituted alkene, the major product results from the addition of the hydrogen atom to the double-bonded carbon that is attached to more hydrogen atoms, while the halide ion adds to the other double-bonded carbon. So to sum it up, this Markovnikov rule tells us that when we are dealing with an asymmetrically substituted alkene hydrohalogenation, we should always remember that the hydrogen atom will be attached to the carbon that has more hydrogen atom attached to it, while the halide will be added to the other double-bonded carbon, or to the carbon atom that has lesser hydrogen attached to it. This arrangement creates a more stable carbocation intermediate. So, you already have an idea of the Markovnikov rule, which means that you already know how to write the product when we're dealing with a symmetrically substituted alkene and also the symmetrically substituted ones. But to give you an idea on what is really happening within the hydrohalogenation process, let's break it down into different steps. So here, I'm going to discuss the alkene hydrohalogenation mechanisms. The first step is the dissociation of hydrogen halide. You already know what a hydrogen halide is. So this is what the alkene is reacting with in the process. So for example, we have a hydrogen halide here, hydrogen bromide. So the first step in the hydrohalogenation of alkene, we are going to dissociate this hydrogen halide into two separate atoms, which is the hydrogen atom and the bromide atom. After we had dissociated the hydrogen halide, we are now going to the second step, which is the formation of the pi complex. So, as we can see in the picture given, we have here a propene, and here is the pi complex that we're going to form. So first, as stated in the Markovnikov rule, we're going to utilize the proton, which is the hydrogen atom. So when we add the hydrogen atom to the propene, the pi complex will be formed. So this hydrogen atom here will now attach itself to the double bond so that it can have its way to the carbon here. So that's basically what is happening when the hydrogen atom attached to the carbon atom in the hydrohalogenation process. So after the formation of the pi complex, we now have the third step, which is the breaking of such complex. So here in the picture, we can see that the pi complex here was broken to formulate these two products. So the pi complex breaks, creating a single sigma bond between one carbon of the double bonded pair and the hydrogen. So this hydrogen here can create a sigma bond between this carbon here, the second carbon, or this carbon here, the first carbon. It's either the two. So this is what happened when we say the breaking of the pi complex. So we can see in this diagram that the first carbocation product was created because the hydrogen connects itself to the second carbon. So from CH here, it becomes CH2. Then the first carbon here undergoes protonation. It gains proton because the pi bond was broken. So this creates a proton gained by the first carbon. So in the second carbocation product, we have the hydrogen that connects itself to the first carbon atom, making it from CH2 to CH3. Then, the second carbon undergoes protonation because the pi bond here was broken. So, it adds a proton here. So, that is basically what happens. So, this happens because in an asymmetrically substituted alkene, two different carbocations are possible. The major product is generated from the more stable carbocation, while the minor product forms from the less stable one. So that's what happens. Thus, the major product is 2-bromopropane because the bromine here, after the hydrogen already attached itself to one of the carbons, then the other carbon that has excess proton or the carbocation will attract the halide. Thus, it will connect itself to the carbon and will create the products of the hydrohalogenation. So first, we have here 1-bromopropane will be the minor product. And here we have 2-bromopropane will be the major product because the bromine here will attach itself to this second carbon here. So this is what is happening in the hydrogen. Going back, we already discussed the basics of hydrohalogenation. We already had tackled the hydrogen halide and all about it. And now we just had finished the hydrohalogenation of alkenes. So that's it for this video. I hope you understand something about hydrohalogenation of both symmetrically and asymmetrically substituted alkene. And see you soon. Thank you.